So it's my utmost pleasure to introduce you Professor Aaron Ames. I mean, I feel so awkward to say professor since he's like my adopted son. Aaron and I kind of met 2003, something like that. Aaron was a student of Shankar Shastri. As some of you may know, Shankar is the Mr. Theory. And so at one point, we discussed category theory, which is really far up there with Aaron. And then I said, well, listen, you are getting a degree in computer engineering. Validation of the theory is in order. And I said, I will help you. So I connected him with my student, Ram Vasudevan, who was studying walking. And indeed, Aaron and Ram did some basic experiments in human walking and how to model human walking. But that made him, I think, to convert to start to think about building. Oh my God, look at this. You are popular.
I guess so. Okay, we've got...
Well, sorry, folks. Yeah, find some chairs. I mean, professors will find you some chairs. Anyway, so Aaron then, based on that, started to think about building walking robots. And I believe he has been building them ever since, correct? But Aaron, unlike some of these people who just do, let's try this, let's try that, he does also a systematic analysis and model, and you heard me the word modeling, right? Model of dynamics and how to design these robotics legs so that they have some stability. And believe me, as I get older, I need to hold on in order to have stability. So I appreciate stability, but also efficiency and cost in walking. So without you, he's now, I didn't tell you, I mean, he left Berkeley. He went first to Texas A&M, then he went to Georgia Tech, and now he is finally, I think, completely settled at Caltech. And it is really my pleasure to have him here. He's just a wonderful friend and colleague and super, super smart. So ask questions.
Thank you. Thank you for the wonderful introduction, Rusna. That was a fantastic introduction. Thank you all for coming. I see we have a full house, so I'm very honored and flattered. It's fun to be back at Berkeley, roam the halls I did as a grad student. You get kind of whiplash because you remember where your mindset was then and where it is now as a professor, and it's an interesting experience to see that gap. And of course, Rujna giving the intro is very fitting because, as she said many times, and I'm very proud to say, she got me into experiments. So it wasn't until I worked with her that I did an experiment at all. And that was when I was already a professor. So all this stuff has happened since then, because you'll see a lot of experiments, but you also see a lot of math. And of course, along with her, all the things in this talk are due to great graduate students I've had over the years, great collaborators I've had, including Rujna and Kaushal, who's here, and everyone else. So this talk is a compendium of a lot of people's results that I get to talk about. So as many of you probably did, grew up on science fiction, still read it to this day, I hope. You never lose that marvel. Science fiction has obviously promised us a lot with robotic systems and what they could do, from humanoid robots that, deliver mail, walk the dogs, and even at the end of this, they hug kids, so there's the human-robot interaction part, all the way to autonomous cars, robots that explore space, right? This is off some pretty hokey 2000 movie with Val Kilmer, where this robot actually tries to kill people. But what's interesting is this robot actually has a helicopter that takes off. and explorers. And if you know, Mars 2020 mission will have a helicopter on the rover that will take off and explore. So sometimes fact mirrors fiction in interesting ways. And of course, robotic-assisted devices and exoskeletons, right? So all these have kind of driven our imagination of what robots are and should be. And in that context, where are we today now with this kind of image of where robots should be? And the question, or the answer to this is a little funny. So I had a lunch with a bunch of grad students, and they convinced me to change the first slides in my talk last minute. So in between meetings with students, I put these in. And the idea is, here's where we are from an AI perspective. And I think Berkeley's a fitting place to do this. There's been incredible successes recently, and you see the headlines, right? Like, supercomputer learns 3,000 years of knowledge in 40 minutes, and everything's won, or 40 days, and AlphaGo beats the Go champion, really impressive. And of course, this video a little while back went super viral because it learned how to walk all on its own, right? End-to-end learning. So this is sort of what everyone is talking about right now, right? And in fact, this spurs a lot of public perception, right? Like, how many doomsday articles do you read? Every time I post a YouTube video, you know, Skynet is here. And it's really funny to see that the public really doesn't know what's going on right now, right? And in fact, if you read these headlines, things like this, they warn about artificial intelligence. And the subheadline is that Google-owned Boston Dynamics releases this video that does something, right? So there's AI and Boston Dynamics, right? And I think some people know where this is going, right? So AI is proved very successful in the purely digital world. But let's look at the successes on robotic systems. We have Boston Dynamics that everyone knows doing backflips and running, and this is really impressive from a robotics and control point of view, right? To be a little bit self-serving, you know, I have robots walking around Caltech. I have exoskeletons walking paraplegics around. So we've done a lot on the robotic systems side. So the question always comes, how much of this uses AI? Very good. Very good. By most definitions, the answer is 0. But it depends on your definition, and we could quibble about this. But in the standard notation of a deep neural network or some sort of machine learning of this form that's popular, these all use robotics and control, right, as their core thing. Now, I'm not advocating that's the only solution, but I think it's important to recognize this. And why is this the case? Because the reality is that nature is brutal. Mother Nature doesn't care if you don't know what you're doing. She'll smack you down and make your robots fall. This happens to Boston Dynamics all the time. You've seen all the fall videos. I like this one especially, because it's just like a compendium of failures. And then it goes again. All right. Of course, it happens with the backflip. And I give Boston Dynamics a lot of credit for showing their outtakes. Because what you probably all know is for every beautiful video that you see, even in this talk, there were 10,000 videos that failed and before and 10,000 that fail after. And you get to see the one perfect moment in time when everything runs out. And just to show that I'm not picking on everyone else besides me, this was Cassie walking in front of Caltech, and we saw these students, and we were doing a shoot, so this is a great shot. They pull out their phones. I feel totally comfortable. I'm back off scene here a little bit. And then I saw this oscillation, and then just faceplant. And at that point, my only reaction as a seasoned roboticist was to kind of go like this, because that was going to help somehow, right? So we're all subject to nature smacking us down when we think we're doing what we need to do right? So where does this lead to? And this is the message I wanted to I changed to and I want to make, is that here we live in our dynamics and control world, where I love living. We have theorems, we use models, we have proofs, everything's beautiful. Until sometimes you go to hardware and then it's really brutal and realize you don't know anything, right? On the other hand, you have what I call the mind, which is learning in a general context. What I would actually call this is data-driven methods. Things that use data in the absence of models, right? And my argument is these need to come together. So what I'm saying is we need to have, a peaceful get-together of when we know the models, let's use them. When we don't know models or we only have data, let's exploit that in the context of these models. Right? So that's my sort of pitch in terms of AI and robotics to kind of address the elephant in the room. For most of this talk, I'm going to live squarely here. I'm not a learning person. So I want to talk a little bit about what this means, and then I'm going to connect it to the bigger picture at the end. So again, we have these beautiful theorems that build on all of this previous work that's happened in control over the years, and also robotics over the years, going back to the 80s, feedback linearization, control the optimal functions. Of course, one problem that control theorists have, so I'll make fun of them a little bit too, this is being recorded, so I need to be a little careful, is they develop this wonderful math and theory with no notion of whether it will work on hardware, right? It's all about the beauty and the understanding you gain, which is very useful. But if it doesn't work on hardware, how accurate is your theorem really? Right? So the question is, how do we pull these things together in dynamics and control? So I'm going to begin with giving everyone, I think, approximately 15-minute tutorial on nonlinear control. Who's had a nonlinear control class? Okay, a good third of the audience. So you guys will find this very basic. For you people that have not, this might be a little enlightening. So the challenge was the following. The challenge was to develop a robot that's an order of magnitude more efficient in walking than Boston Dynamics. So, question? No? Okay. Okay. Yes, you guys will see this if you haven't yet. And so the challenge was to get more efficient walking than Boston Dynamics. And the only way to do this was to exploit all of its inherent dynamics all the way down the chain. So how does this work? So what is nonlinear control of walking robots in a nutshell? Okay, so the ideas are actually really simple, so I can give them to you in a not too complicated way. What you do is you start with a desired behavior on your system. You have an actual behavior, meaning these functions calculated on your robot. You try to drive them to be the same. When you drive them to be the same, the end result is a simple reduced order model that captures the essential behavior of your system. Right? By the way, a shout out to Ruzhin. These were the first experiments I ever performed right here, 2011 at Berkeley, with Ram sitting back there looking very bored. So we're all, exactly. So what does this mean? Well, again, just more mathematically, we want to drive the signal to zero, and by doing so, we projected this surface, right? This is what's called the zero dynamics if you've had nonlinear control. Okay, so the question then becomes, if this is our objective, drive some output to zero, that's sort of the canonical objective in nonlinear control, how do we do that? Well, the first step that you'll often take is to say, look, if I take this output and I differentiate it twice in this case, you're going to get a bunch of nonlinear dynamic stuff, Lie derivatives, right? And your output will appear here. And if you're lucky, what's going to happen? This matrix will be invertible. And you can say, I'm going to invert this matrix, cancel out these dynamics with my input, and the end result will be a double integrator, right? Once you have a double integrator, we know how to stabilize this system, right? It's pretty simple. You can define a whole wealth of feedback control laws that stabilize that linear system. So this is kind of the graphic of the stability down to this surface. In fact, one way to do it is to write that system as a control system, a linear control system, right? And now you have a nice F matrix, a G matrix. They're controllable. You can do LQR control. You can do anything you want to do, right? And once you pick this mu, that gives you a feedback on these X dynamics. Those X dynamics include your output and their derivative. So by driving these X dynamics to zero, you're driving Y to zero and its derivative, right? And what you're left over with is what's called the zero dynamics. That's the passive dynamics of the system that you can't directly control, right? So we've defined this paradigm. Alberto, hi. And from this paradigm, we can actually prove properties of the system. We have a theorem that says as long as this is stable, since we can stabilize this, the combination of the two will be stable. That's not particularly surprising, right? Everyone with me? Okay. That is really the first term of nonlinear control in a very concise box.
What do you mean by that, the zero dynamics?
I mean that you can, so these are your outputs. Your outputs are chosen so they're associated with actuators in your system, which means that this system is sort of controllable. So this is the part of the system you can actuate, and you use that actuation to stabilize it. What's left over are the coordinates that are sort of normal. This is called normal form. Normal to your actuated degrees of freedom. So these are the passive parts, meaning the part you can't directly control with an actuator on your system. That's what I mean by passive, okay? All right, so that's how we get to stability. And in fact, this theorem and its offshoots have been implemented on a whole bunch of robots. So this is actually the first robot I ever built. I keep it here for sentimental reasons. Amber 1, Amber 2. This is a prototype to a humanoid robot as well. So I wanted to kind of give this primer because what is it that we did here? This is sort of, again, this is nonlinear control in a nutshell in some context. We started with a nonlinear system. We feedback linearized it. And then we stabilized the system. Great story, right? What's wrong with this picture? So I wanted to give everyone that quick overview because there's something inherently wrong with what I just did. Something even kind of offensive about it. What is it? Let's forgive that. Let's assume you have a perfect model. Yeah, if you have modeling errors, it's a nightmare. Something deeper than that, though. Yeah? You can't. That's correct. That's correct, but I'm looking for something a little bit deeper.
Sometimes even in principle, you can't cancel out the nonlinearity. Like that, you might not be able to.
You might not be able to invert that. That's still not what I'm quite looking for. The control can be unbounded. These are all true statements, but none of them I'm looking for. We're taking a system that's nonlinear and beautiful, that has its own inherent dynamics, and our answer to that system is cancel out everything that's nonlinear about it. Make it look like a linear system because that's what we understand. So we're fundamentally destroying the inherent properties of the system, right? See what I'm saying? We're making it look like something we know, even though that thing that we know might not be the best thing. In fact, what we really want to do is capture the inherent dynamics of the system. So how do we do that? We don't want to cancel out everything. We want to exploit the property we have, or that we want to achieve. We want to make a Lyapunov function decay. Right? So if we consider this problem instead, now the goal, and I'm going to describe this in 1 second, the idea is if we can make this v dot decrease in the proper way, meaning exponentially, this is now a one-dimensional system. Instead of here, we had a full n-dimensional system where we're canceling out everything. Finding a u that does this means we're only going to be modulating this v dot subject to our control objective rather than canceling out everything in the system. It's a much better way to go, right? Everyone believe me? Okay, so let's go through the math really quick. So again, just to recap, we have our system in normal form. This part is controllable, and this part is passive. So we have our x dynamics and our z dynamics. A Lyapunov function is a positive definite function. So think about it for our intents and purposes as a bowl. Okay? And Lyapunov theory is very simple. We have a bowl. Our objective, y equals 0, is at the bottom of our bowl. As long as our derivative decreases properly, in this case subject to this bound, then that's going to guarantee that our Lyapunov function will decrease exponentially. But it's a positive definite function, so if this decreases exponentially, so does our state, which is our air dynamics. So that means we'll have exponential decay of our air dynamics, all through a single inequality, a one-dimensional inequality. Right? So the way I think about this is these fair games, right, where you put the coin in the thing, spins down. Who's played these? So I was at I took this video myself at the Minnesota State Fair, and I was super excited, and I took a picture of this with my wife because I was super excited because I'm like, this is Lyapunov functions incarnate, this is beautiful, and everyone thought I was super weird. I was the only person like over 12 putting coins down this thing. But that's what Lyapunov looks like. But there's something else that goes even deeper here. We can actually characterize all of the controllers that are stabilizing now. So before we picked one in some sense. We picked the one that canceled out all the dynamics, right? Now we can say that, look, if we can find an input that makes sure our Lyapunov function decays in the proper rate, then we can have a whole set of controllers for which any controller that satisfies this inequality will make sure we get the proper convergence, right? So we have a set of controllers that stabilize the system. Yeah? And you can even do a hybrid systems version of this where you add an epsilon that's sort of exponentially stabilizing at a rapid pace. And then you can actually make guarantees that, in fact, we can stabilize these hybrid system models of walking robots. I'm not going to talk about that in that talk, but these exist. Okay, so this is our controller now. Now, the question becomes, how do we implement this controller? And how do we synthesize this controller? So the question, the knock on Lyapunov is typically, well, we can't actually find them, so it doesn't matter that there's a theorem that says they should exist, right? Who's heard that before? Huh? Okay. Yeah, well, he's incorrect in this case. Okay, exactly, I wish he was here. And so actually, it turns out that, and I like showing this because there's a methodical way of constructing them in this case. So let's go back again, and this is kind of cool, so just bear with me for 1 second. So we canceled out our nonlinear dynamics to get a linear system. You say, why am I back here? Just bear with me for a second. This linear system has a Lyapunov function, right? Because it's stable, okay, or controllable, or whichever way you want to view it. So what that means is for the linear system, this becomes our inequality constraint in terms of our auxiliary control input. Our mu, not our u, which was our real control input, right? So all we have to do is find a mu that satisfies this, and we can plug it into here, and we get a U. Of course, this still defeats the purpose because we're still running it through our feedback linearization, right? But we could pick the best mu, the one that minimizes the norm, the minimum norm U that satisfies this inequality, right? So that's like taking and saying, I want a favored direction that minimizes my input. Okay, but we're still not there because this mu is for our linear system that has no bearing on this nonlinear dynamics of the system, right? But this suggests something interesting. This is actually a quadratic program, right? Because we're trying to find the minimum U subject to a single inequality constraint that's affine in our input, right? And this is a valid feedback controller. In fact, it has an explicit closed form solution using the KKT conditions, right? It's called the min-norm controller. But by putting this as a quadratic program, all of a sudden a little magic happens. Who can guess this magic? You can do that. That's not what I'm looking for. You can untangle the mistake we made. We can correct our error. And our error was to feedback linearize the dynamics. We can unlinearize. And note that, in fact, we have an affine relationship between U and mu. We can plug that into this inequality. And now we have a single inequality constraint for which our nonlinear dynamics are introduced back into the system. And in fact, this is a proof I just gave you that this is a valid control Lyapunov function for the nonlinear system, not the linear system, right? And this encodes the derivative condition that we decay for our Lyapunov function, and it decodes the natural dynamics of the nonlinear system. So at every point in time, you'll pick an input that's consistent with the inherent dynamics of the system rather than forcing the system to do something you don't want to do, right? Everyone with me? Okay, so this actually works on hardware too. So this is results with Kaushal, and I like keeping this video. It's from 2015, so it's an oldie but goodie. 3 years ago, I know is a long time in the robotics world, but we're actually able to implement both feedback linearization and the CLF, and you find that in the case of feedback linearization, you get these high oscillation torques because you're forcing the system to do something it doesn't want to do, while here you get much smoother torque response. So we've also done this in the context of humanoid robots, meaning we can extend this to very complicated systems. Yeah? The inverse here of the decoupling matrix? You're talking about here? Yeah, that matters too, actually. In fact, you can at least relax the conditions that the decoupling matrix be invertible now, right? And in some sense, you're calculating a pseudo-inverse, right? Which can be calculated by a quadratic program. So yeah, it actually does matter. It's a good observation. There's a lot of little things here. We had a torque bounds too. There's a lot of little details under the hood that's actually really nice when you get exposed. You can, for example, do multi-objective control. Take multiple CLFs and you can balance multiple objectives at the same time, right? So it opens up quite a few things. Again, so now I'm going to go back to the robotics world. I've given everyone their dose of nonlinear control for the moment. And we applied this to Duris. So Duris in this case has this multi-domain hybrid system model. And remember that these outputs, we wanted to drive them to 0, for which we had a theorem that says everything is good in that case. And we did that by a Lyapunov function. It turns out from these outputs, we got the Lyapunov function, right? So generating the outputs are where all the computation will happen. Once you have the outputs, you get the Lyapunov function. Now, these outputs need to be calculated in such a way, meaning these parameters need to be chosen, so they respect the conditions of the theorem, right? So it turns out that you can actually, and I'm going to be brief here, but one of my students, who's now a professor at Ohio State, developed a toolbox using collocation methods together with this, actually making it computationally feasible to calculate these really complex conditions for humanoid robots. So the idea is you sort of dice up your space and your conditions, you solve this much bigger problem, and that makes it much more efficient. So just to show you a couple examples, he implemented this on a walking robot. So in this case, the treadmill is changing speed. And what you're seeing is the trajectory generation running. What you're actually generating is the Lyapunov function in about a half of a second increment. So that's the computation gap. So in about a half of a second, we can measure the speed, generate a gait for that walking speed. With that comes for free a Lyapunov function, a control Lyapunov function, that we then put on the robot to walk at that desired speed. So we're at onboard, not real time, but onboard gait generation using these methods. The same things applied to Duris, this humanoid robot I showed you earlier. In this case, it takes about 5 minutes, 5 to 10 minutes to generate a walking gait using all these conditions that I told you about. And the end result is pretty smooth walking. I mean, it's pretty natural walking. And it's important to note that in this case, Duris has springs at the ankles. So you have passive dynamics. The zero dynamics represent this movement of the entire base of the robot, which is a very non-trivial condition to have because it oscillates up and down. Right? And that's when the battery's turned off. So we actually took this to California a couple years ago for the DARPA Robotics Challenge and implemented it in front of a bunch of people. We had like 2,000 spectators come by and watch this robot. And the reason why I bring this up, and I'm being a little fast, but I wanted to just kind of show this slide. So I just went through the development of all this math. I slowed down a little bit on the development of the control Lyapunov function because I think that's the important part. Then I just sped through slides where it actually works on hardware. And this worked on hardware really well. In fact, this is the most efficient walking at the time ever realized on a humanoid robot. Cost of transport of 1.6. And we had sustained walking for over 2.5 hours continuously on this robot. Right? Meaning this wasn't a one-shot video, but this thing would run and run and run. That was great. But to do that, I want to be fully honest. And the honesty is that the perfect clean mathematics accounts for about 83% of the trajectories. So even though I had this wonderful theorem and we have this computation engine, there's still about 20% gap between what the math told us and what actually worked on hardware in the end. We had to tune all this stuff in to handle uncertainties of signals, etc. So again, the lesson here is there is a reality gap on robotic systems. And no matter how beautiful the theorems are, or not, depending on your opinion, we need to address this reality gap. Okay? So on this robot, every joint was active above the ankle here. So the only passive dynamics were at this spring right here, which is actually really beneficial. It means that we had a two-dimensional zero dynamics that was actually normal to the forward stability direction. So you could actually essentially show that this is stable for arbitrary incarnations of your outputs subject to the constraints that they're hybrid invariant. That was a dump of some of the math under the surface. But it actually was a really nice design. And this, by the way, we designed with Jonathan Hurst and SRI exactly so it would have this nice stability properties with respect to the mathematics. Okay, so there's still some stuff to address. Okay, so what I did, that's a good question. So what I did is the desired trajectories are the ones given by the theorem. Okay, and what I did is I looked at, the desired trajectories are here. The deltas are how much we had to perturb those trajectories to stabilize the system. So what we did is, on top of our nominal controller, we added these sort of robustifying regulators. So for example, if the torso was leaning, the leg would kick out a little bit. We had no justification for doing that except it made the walking better. So we looked at the magnitude of those perturbations and calculated how much it was modifying the nominal trajectory. And that was our metric to how much we were perturbing. It's not a great metric, but at least it shows. So the shaded region is our nominal perfect theorem trajectory, and this is all those regulator stuff we were doing on all the different joints.
The better metric, time divided here versus time.
So I would argue the better metric is maybe the time it takes to actually get the theorem to work on the hardware, once you have the hardware. We got this. But in the lab. So we had to make these modifications to get it walk for 2 hours continuously in a demo. In the lab, we actually implemented it cleanly, the earlier video, and that only took us 3 weeks from the time the robot arrived in our lab to getting the first dynamic walking on a humanoid was 3 weeks. And so it's because of the math. So I think math saves you ultimately a lot of time when it's done right. Okay. Yeah.
So I agree that feedback linearizing control isn't quite natural with
Yeah.
internal dynamics. But just keeping the Lyapunov function and throwing away the controller, I'm not convinced that makes it any more natural because you're still using an energy function that doesn't really correspond to the energy.
So feedback linearization, again, what you're doing is you're taking and canceling out all of the nonlinear dynamics. And then you can do anything you want after that. The Lyapunov function says, what I care about here in this case is stability, right? Right, yeah.
It's just that the Lyapunov function may now be a little unnatural because it depends on variables that
No, it may be, except now what you're doing is requiring your control input. In the case of Duris, I think it's something like 20-some dimensional input vector that only has to satisfy a single one-dimensional inequality constraint. So the point, what I'm saying, well, on the other hand, feedback linearization, you have to have all 20 of those terms line up perfectly. So even though you're right, I'm not saying in no way did I claim that this is the optimal capture the dynamics perfectly. I would argue it's better dramatically. Yeah, but it's still not the best, and the best would be finding good Lyapunov functions. So I'm also not saying we should abandon the search for good Lyapunov functions. The better Lyapunov function, the better the control in this context, right? So these are very good points. Yeah, and the better your function, the more you'll be attuned to the dynamics of the system. Absolutely. This is a very good point. Anyways, I just wanted to note that after the challenge, we extended this to in a couple of regards. We got a robot to run using the same general mathematics. So this is a planar robot, which means it can fall forward and back, but stays upright. I just think it's kind of a pretty motion, so I like to show this video. Running's really hard, by the way. Making a robot run is really, really hard. Because the flight phase, you have no control over the system, so you have to kind of land perfectly, right, every time. And we also extended it to multi-contact walking on Duris. This is probably my favorite walking that we've generated so far, because we get this nice heel strike and toe strike behavior. So this very natural human-like walking, which, by the way, increases the dimensions of your passive dynamics when you go up on a toe. Right? And I think it's cool to kind of show that the data, we actually compared this walking of Duris to the data we collected in Berkeley back in 2011, and found that relative to a metric on the graph, and I won't explain the details, Duris is actually human-like, meaning you can't distinguish it from human walking in some metrics. So that brings back to those experiments. All right, so I wanted to do all this control generation because now I want to get to safety. And there's no way to talk about safety without understanding stability first. They're duals of each other, right? So safety is obviously becoming an incredibly prevalent and immediate concern. A lot of people are working on it. Claire Tomlin has a bunch of people, and I think it's a fantastic problem as more of these autonomous cars crash, which you know they're going to do. We need to understand how to handle these scenarios. And actually it was Kaushal that did this great problem called the stepping stone problem as a way of kind of capturing what it means to have safety and what that means when you put it together with dynamics and stability. Right? So in the context of the stepping stones, it's a very clear problem. You have water, you don't want to fall. You need to dynamically jump between these different stones. And humans can do this with amazing ease. This guy's like carrying a baby, holding the hands. I mean, it's pretty impressive what humans can do, right? So in the context of robots, what does this mean? So at a basic level, if you want a robot to walk on stepping stones, you have to have control objectives, which I already showed you can be encoded by Lyapunov functions, but you also have to have safety constraints. And how do you put these two together? And that's phase 2 of this. So the idea is actually very similar to Lyapunov, so I can actually be fairly brief with it. But it's slightly different, so don't confuse it with Lyapunov. All right, so the idea is safety in our context, and this is not the only definition of safety, is keeping a set invariant in your system. Right? So you can imagine your set, in this case the set would be the circle, defined as a super level set of a function h. Okay? And the goal is to keep the system within this set. Right? So just like with Lyapunov, you can find derivative conditions on h that keep it safe. So it's important to note that this is a bit different from Lyapunov. So first, h is not necessarily a positive definite function. It just defines your safe region. And second of all, this inequality is conspicuously flipped. And what that says is as you approach the boundary, you have to go tangent to the boundary, but in the set, you don't make sub-level sets be invariant, right? So you can let the system wander all the way to the boundary, and then you say you have to stop. And so just like with Lyapunov functions, or actually this is an illustration of what it looks like to stay within this set. So just like with Lyapunov function, there's a control variant. Okay, and the control variant says the following. If we can find inputs that satisfy this inequality, then there's a whole wealth of inputs, meaning any input that satisfies this inequality will keep the system safe. Right? So we have a whole collection of inputs. Right? And in fact, just like we had with Lyapunov, we can write this as a quadratic program. Only in this case, it's slightly different. Now we're saying we want to satisfy this safety constraint subject to a quadratic cost. In this case, you might want to say, I want to find the closest input to some other control input somebody else gave me, subject to being safe. Right? So this is a pretty basic framework for safety critical control, but is pretty applicable. In fact, it's in some sense the best characterization you can have because it's actually necessary and sufficient. You don't have to read all these theorems. The point is it's necessary and sufficient, right? And we can prove it as such. Moreover, it takes you a little bit further than you might expect because we can bring together safety and stability all at the same time, meaning we can balance these two objectives. Okay? So here's our safety controller. How do we bring in stability? You guys will nail this one, I'm confident. This is Berkeley. We want to add a, so this just says our system is safe, meaning we say within a set. How do we make sure we're stable at the same time to some point? Yes, everyone nails it. Throw in a Lyapunov function. We already had an inequality constraint here. Let's just add these together, right? And now you're going to have to be a little careful because you're going to have to relax your Lyapunov function because you might not have a solvable problem. If your equilibrium point was outside of your safe set, you're going to conflict. So you have to decide which of these two is more important to you, safety or stability. But it lets you do them both at the same time, right? So you can unify them together. Good? You see why I went through the Lyapunov stuff, making sense on the back end? Okay, we're home free now. Bunch of movies. All right. So here's what this looks like in action. So we have our safe set now. Our safe set is keep the segue between plus or minus 15 degrees, right? And what we're doing in this case, there's no Lyapunov function, but this QP is running on this in real time. And we just do a standard PD control to keep the pendulum upright. Okay? And then we kick it. So by the way, the story with this is that I got on a Segway for this thing for the first time. I just about killed myself. So I got on and then I was like, all right, I want to slow down. And I went to pull back like you're supposed to, but I leaned back and ended up creating a larger angular difference. So the Segway just shoots out. And I was like, all right, I'm not getting on this thing again until you can prove to me mathematically it's safe, right? And so this is what it looks like. So the kick is without it and this is with it. I mean, it works. It's kind of self-explanatory, right? But I think that's a pretty video. So we've since carried these ideas to stepping stones. This is joint work with Kaushal. So this is just another shot, but it's pretty cool. So by the way, in this case, we do have a Lyapunov function, which is the walking I showed you demonstrated on Duris, and then we add the barrier function. And so all of the movement modulation is solely a function of the barrier function modulating the foot placement of the robot, right? So it's not a planned motion. It's a reactive motion to the things moving around. I've also worked at Georgia Tech with Magnus Egerstad on applying this to multi-robot systems and swarms. So in this case, you can define sort of safe regions around all the different agents, synthesize barrier functions that encode those safe regions, right? And for example, this is 50 robots, and they're told to go directly across the room, just a straight line. Naturally, straight line with two robots is going to mean collision. So all of this movement you're seeing here is a function of the barrier function just reactively moving them around so they don't collide. And that you get this weird swirling behavior. And ultimately on the back end, when they're finally free, they can go to that position they wanted to go to initially, right? So this is kind of putting those pieces together. We can also do it for more interesting systems, so drones in this case. So here, a grad student is flying this one, and these are on autopilot, following a trajectory. And the whole objective of the grad student is to crash the drones, right? So he's trying to ram his drone into those drones. And the only thing preventing them from crashing is a barrier function that's like a force field, right? It's like a very Star Wars kind of force field thing around the drones, right? It's actually cooler when they go faster. And by the way, we're using differential flatness and everything here, so we're actually explaining the nonlinear dynamics of the system in the process. Actually, Kaushal has good work on this stuff for drones as well, for nonlinear systems. And finally, just to show you, the real world will always smack you down, the outtakes. So what was happening here? By the way, why did this fail? I just said I have a theorem that says everything's safe. Why did it fail? That's actually not. That could definitely be a cause. And in fact, that could exacerbate what actually happened. Boom. Motion capture can drop out sometimes. You lose a couple packets, it doesn't know where it's at. Imperfect sensing. Imperfect sensing, no matter how good your math is, if you don't know where you're at, you're dead, right? So it's important to keep these things in mind. Finally, we're actually working to extend these ideas to cooperative control of multiple heterogeneous robots. So this is actually, again, motivated by the Mars 2020. So you have a rover and a helicopter. So the idea here is we actually use barrier functions to get an abstraction for the system, if you know formal methods. And then we can plan over that abstraction in essence. So here the rover comes out, the drone takes off. This is all autonomous, by the way. There's no one controlling it. It goes out and explores the space, figures out where the sample is that you want to take, the scientific sample, comes back and lands on there it goes, and then this thing drives off and finds where it wants to go. Again, it's a very slow experiment, but we're starting to try to push to do much more rich autonomous behaviors, right? And that leads to the next steps. So in the remaining few minutes, I kind of like powered through the first part of the talk. I know that was a lot of information, but I want to get everyone to hear all these things. So the next step is, where do we go next? And autonomy is kind of you've heard it, it's the big keyword of the moment, but there's a reason it's a keyword. And it's really important. It's about how do we get robots out of the lab now? Again, the couple failures I showed you all had one thing in common. We had bad sensor data, or we have bad models. And the thing is, when you take a robot and you throw it in the real world, you're going to have lots of bad sensor data, lots of bad models. You're going to have terrible interactions. So how do we start to deal with that? And this is where I'll come back to learning. So I said we need to bring the mind and body together. And again, this is a very high-level characterization. Ben's complaining. This was my slide, inspired by John. This is, by the way, for those that don't know, this is a classic John Doyle talk. And you'll see that, there's always the quadrant. It's coming, it's coming, it's coming. I got to represent Caltech a little bit. All right, forgive me. All right, last one. So we, of course, have a bunch of successes in the purely digital world for learning. We have a bunch of successes on the purely mechanical world for control. And obviously, there's systems that are living at this intersection. So obviously, where we want to be is here. Ben spent too much time. Oh, so we have a new center for autonomy at Caltech. CAST Autonomy. Sorry, I should explain this. We want to live here. This is high-level stuff. But the message is clear. And then there's this cool animation. It all looks very snazzy. I'm sorry for this high-level stuff, but we earned our stripes through the nonlinear control part, right? So we feel like this is not too much fluff. So the idea is we want to bring together learning. And so let me actually just explain this on real examples, because it's very fluffy what I just said. All right, so the idea is, first, how do we characterize autonomy? And this is, I think, a good way of thinking about it. Let's think about all the ways in which robots would go into the real world and their functions and roles they would play. And let's try to understand the systems in that context. So let me give you a very concrete example. Explorers is what we call it. And the idea is, again, I want to get my robots out of the lab into the real world doing complex things. So let's go one step more concrete, and I'm going to pose a challenge problem that I have no idea if we'll ever solve in my lifetime. But I don't know if you know, but there's a trail that goes from Mexico to Canada, right? Called the Pacific Crest Trail. So imagine what it would take to have a robot traverse that trail autonomously. Just think for a second about all the problems we'd have to solve to make that happen, right? This is what we call a moonshot, right? It's a very hard problem. For example, you'd have to scale a wall. That's not very hard. And then you'd have to keep going all the way up to Canada, right? Okay, no one laughed at my joke. I usually get a good one. Don't broadcast this on YouTube, please. So the idea is, you'll have to do everything from planning, learning, dynamic walking, locomotion on diverse terrain. So let me zoom in one more bit. I started really high level. Let's get a little more concrete. Let's just look at the walking for a second. So what are we going to have to do to realize this? Well, if you look at your robot, the internal dynamics of the robot you essentially know perfectly, okay, for all intents and purposes. What you don't know is this reaction force interfacing with the real world. So you can actually write your dynamics in a way that your unknown parts of the model and the system with the real world are isolated as this additive term. And importantly, this is the affx is the external forces at the contact points. Yeah, at the contact point. So everything else this is a Jacobian projection. So no matter how high dimensional your system is, your contact forces are the only thing you don't know. And that's what you need to learn to handle all these different terrain types, right? So it turns out that hard ground is easy to model in terms of contact, but granular media, meaning sand and dirt, is actually almost impossible to model. There's people that have whole labs devoted to this. And so let me show you how that works. So if you take a walking robot and you put it on hard ground, it walks fine. Put it on sand, and this is what it will do. Yeah. Because the model's just totally wrong, right? And it's the same model internally we had before, and that worked fine, right? But it fails. So the idea is what you can do is start to use learning in a loop. And learning I'm using very generally. In this case, we're talking about Gaussian process regression. We start with an assumed model of the system. We actually run this through experiments. We look at that data. From the data, we iterate our model of the world, update that model in our control framework, apply it experimentally again, and repeat. So in this case, we're able to actually get this thing to jump in sand and dirt. This is joint work with Patricio Vela at Georgia Tech to a desired height. If you modify the reaction force models of walking robots, you can get them to walk on sand and dirt as well. So this is the same robot, the same sand, but now that we've updated models of the world, we can walk on it, right? So that's how learning and control and dynamics can start to play a role and be paired, right? And here learning, I mean a very specific form of learning. We're playing with this in different contexts. For example, we recently got Cassie, our Amber, our custom-built robot in our lab, to walk on an oil-slicked treadmill. So we douse this thing, and actually it's like sort of walking on ice. So you see how it slides forward? And we put that planning into the motion so that we can handle this different terrain type, right? So that's actually it's kind of fun seeing it. By the way, if you took a nominal controller and put it on the slick treadmill, it fell on its face every time, right? Walking on ice is not easy. And finally, we're working to extend these ideas to Cassie. So for the sake of disclosure, there's no learning on here whatsoever. This is all robustness of nonlinear controllers, but it's still cool to see where we're able to get in terms of getting this robot outside. So again, we do all the things I said. We start simulation versus reality, make sure there's alignment, test it in our lab, test it on flat ground, and then ultimately put it on non-trivial terrain. Because the goal is to get this thing out into the real world, right? So just to show you how far this can go, this is CNET came. I don't know if I grew up on CNET, like reviews online and stuff, so I was kind of pumped about this. So I'm like, okay, this is a good time to take the robot out and totally have it spill all over the place. Let's see how far we can take it. So we took it on the hardest terrain we kind of figured it could potentially handle, ending with a whole clump of roots, tree roots, just to see how robust it was. And it did okay until it fell. Here's one more shot. Just look at these roots, though. This is hard. Think about doing this blindfolded with no models. I mean, it's dancing a little bit. And ultimately, though, boom. Ring? No. This robot was the ring bearer at my wedding, by the way. It walked up the aisle with a ring on its back. So, yes, I'm really that big of a nerd. I don't have a video of it, though, unfortunately. But this robot walked up the aisle. Right? So in my remaining few minutes, and I'm bombarding you with videos, but I think it's cool. The last step is how do we, what's the point of doing all this, right? And I think a very natural way of applying all these things is to have robots that help people. I mean, once we have a humanoid robot walking, we can take it to prosthetics and exoskeletons, right? It seems like a very straightforward process, and in some ways it is. In some ways it's incredibly challenging. And it actually opens an entire world of soft robotics and how do you interface robots with humans, human-robot interaction. But we've had some pretty nice successes so far, taking our QP-based control, applying it to prosthetics. We've even done it with actual amputees, and implementing it on the system itself. So this is our custom-built prosthetic in my lab, and we're running this QP-based control at 200 hertz on a beagle bone while it's walking. We've even taken it outside and showed that it can be fairly robust to different terrain types, flat ground, upslope, downslope. So again, the point of this is showing that the way we generated the gates in this case was like I showed you before. The controller we're realizing the CLF QP-based controller is running on this device, and actually it works in a reasonably good context, right? Pretty robust behaviors. So, and the final bit is some exciting new stuff I actually did with Kaushal as well, which was dynamic walking on exoskeletons. So Berkeley has a long and rich history of exoskeletons, right? But up to date, no exoskeleton has ever walked with a paraplegic in it without crutches. So who's seen exoskeletons go, right? So the crutches are actually part of the control algorithm. Every time the things hit the ground, the exoskeleton walks. So the goal was, can we actually get crutch-free dynamic walking on exoskeletons? So again, the process was exactly the same. In fact, the math on this exoskeleton is just like what we did on Duris. We worked with this French company, Wondercraft, to implement it on their device. We can make it walk dynamically with a dummy in it, meaning it walks on its own. That's actually harder than what you'll see later, getting it to walk with a dummy in it. It agrees with the simulation and everything. And then the important part is, in France, they actually did clinical testing. So this is an actual paraplegic walking in the device, meaning he hasn't walked for about 10 years. He has a completely severed spinal cord. And this was the first time he sort of walked without the need for any assistance. So these things, and this is multiple. It's actually been done, I think they've been done clinical trials on over 12 patients now, somewhere near 20, where they've been able to walk with the device. So the point is, these things actually have real consequences on people's lives if we do our jobs and bring them out into the real world. And excitingly enough, we now have one of these in my lab. So these were taken about 2 weeks ago. So now we get to play with the Exo in our lab itself at Caltech. So it's a pretty sleek machine actually that they built. So that's the story. I'm sticking to it. I jumped through a lot of things here, but there's a takeaway I'm going to just kind of summarize my takeaways, and don't read the slide because that's kind of irrelevant. So first is, as I opened with learning plays a role, but we need to have learning with dynamics. We need to exploit the models that we have and couple them to use learning for the parts that we can't model. Okay, I see people nodding their heads, so I'm glad there's agreement, right? That's step one, okay? Step two is math matters. Nonlinear control matters. Theorems matter. So what I always say is theorems are like that guiding candle light in the cave. All right? Without a theorem, you're just going to bump in the walls all day. You're going to tune parameters till you can't think anymore. A theorem tells you where to go. Now that being said, I also showed you theorems don't fully illuminate the cave. They just tell you where to go. So you have to be intelligent about how you implement. But importantly, we have to try to bridge that divide. We need to actually illuminate the cave, right? We need to make it brighter. And the way to do that is to, again, bring together data-centered methods together with dynamics and control. Okay? Finally, a bunch of cool robot videos, right? Which is the final lesson. And the fact that robots make people happy is a happy consequence, right? So kids love robots, which is very cool. So I always like showing these videos. So it's really sweet. So before I end, we're just getting up already. Couple fun closing videos, right? Because I think I have about 2 minutes. Okay, so first, you might not believe this, but it turns out that turning or flipping a hamburger with a robot arm is exactly the same as walking. So all the algorithms we did to generate walking gaits, we actually applied them to this. This is a company one of my former PhD students started, Robotics, and we actually can dynamically flip these hamburgers. And it's pretty amazing, but it really worked. Not only did it work, but they actually deployed this in the real world. So there was a restaurant, Cali Burger, in Pasadena, where you could come up and get a hamburger that was cooked by this robot. So I've eaten a hamburger that was cooked by algorithms that we developed in the lab, right? Which was pretty cool. I also wrote in the exoskeleton, so I've written in my algorithms, right? Which was pretty cool too. And then finally, we're pushing for other robots just because I feel like the more robots, the better, right? You never have too many. So we're starting to play with quadrupedal robots. This is actually a ghost robotic quadruped built by Ghost Robotics. And we're going to put all of our fancy stuff on that. We're making robots do fun things. So this is Cassie jumping. Boston Dynamics beat us to the jump, but I think we were second in terms of getting a robot to jump. We actually got it to jump about 7 inches in the air, which was pretty cool. Jumping is hard. Running is hard. Walking is hard. These are all hard things, but it's just a fun behavior. And finally, the goal is to get these things, like I said, out into the real world. So I want to close by just showing robots interacting with people because I think it's such a cool thing. And that's where we ultimately want to be, right? So we surprised this student. We just walked the robot up to her. She wasn't expecting this. And what's funny is she started talking to the robot. It doesn't have a head, it doesn't have eyes, but she just started talking to it and enjoying the process. So with that, thank you very much for listening. It's been a pleasure to be back here.